students go for the next one. It is very important title, design of field winding. In previous we already see the similar title, design of field system. Both are different. While the question asks like different field system design or the rotor system design, means you can write all the 5 steps of the previous title. Now we're going to deal the entire parameters of winding of the field. So the design of field winding. So let's deals with the procedures. So the design of field winding. For this content we have a total 9 steps. Let's discuss one by one. The first one is nothing but a voltage across the each field coil. So a field winding is there. You need to find the voltage here. For this determining a voltage, a common assumptions are there. For a field winding design, you have to relax the 15 to 20% of excitation voltage. So with this content, we can frame the equation. A voltage across the each field coil is nothing but EF. It is defined by, when I taking 80%, when we give the relaxation of 20, I can take 80% into VE divided by P. Or else when I give the relaxation of 15%, which means of I'm going to take a 0.85% of VE divided by P. By using this formula, we can easily predict the voltage across the each field coil. Here, the VE is nothing but the excitation voltage, P is nothing but the number of poles. So that's all for finding your voltage of each coils. It is the first step. The second one is nothing but finding the resistance at 75 degrees Celsius. It's a general formula, R is equal to rho L by A. Based on this content, we can frame this equation, RF, that is that field resistance, is equal to TF into rho L by A. The same thing, TF into rho into, instead of L, it is LMTF. It is nothing but a length of mean turn of the field, then divided by AF is nothing but area of the field. By using this formula, we can easily predict the resistance. For this content, the TF is nothing but number of field turns, rho is nothing but resistivity, the LMTF is nothing but mean length, length of the mean turn of the field coil. Then it is calculated by using this equation. It is not a constant. You have to calculate here by using this equation. It is nothing but 2LM plus pi BP plus 0.01 plus DF. Here the LM is nothing but finding this equation, LM is equal to 0.9 into length. By this multiplication we can find the maximum length here. Then BP is nothing but width of the pole body. Then 0.01 is nothing but a constant. Then D, it's a clearance value. Then DF is nothing but depth of the field winding. By substituting all this thing, you can easily find the resistance of the field coil. Then the third step is nothing but area of the field conductors. To determine the area, first of all, you need to find the voltage value of the field coil here. You have to write this voltage across the each coil. It is nothing but EF is nothing but IF into RF. So RF is already calculated here. So RF is nothing but TF rho LMTF divided by AF. Use this formula and substitute here, and you got this equation. After that, I and T is there now. I is for current and T is for turns. Rewrite this equation into ampere turns. So you got this equation. Then rearrange this equation. You have a AF here. This is the content, area of the field conductor. So rearrange this equation and find a formula for finding area of the field conductor. AF is equal to MMF of the field under full load, then rho into LMTF divided by FEF. So with this content, we can easily find the area of the field conductor. Then a fourth content is nothing but height of the each field coil and the height of the winding. This is already covered in a same field system design itself, but it is not a detailed one. It's a cut short value. So just recall the content. For this content of HFC, it's nothing but the ratio of two things, a total area of the field conductor divided by depth of the field conductor. This equation can be rewritten as HFC is equal to AF divided by DF. So rewrite this equation. You got a height of the field winding, HF is nothing but TF into HFC. So by not a rewrite, by using this equation we can find HFC. So substitute here and find the HF value. One more formula is there for finding a height of the field winding. So HF is equal to ATFL. It is nothing but full load MMF value. So that is steps in the previous content determine the full load MMF, or otherwise it is in the fourth step of determining the height of the field winding in the field system design. The same thing here. So HF value, so divided by SF into DF into QF into 10 to the power of 4 in centimeter. Here the SF is nothing but space factor, finding by using this formula. Then D is nothing but the diameter of the field conductor. D1 is nothing but the diameter of the field conductor with insulator. Then QF is nothing but the loss per unit surface, watts per meter square. Just go with the next one. Your fifth title is nothing but finding the value of field current. A current calculation, it is obtained from the same second step itself. We already finding a resistance in the second step and voltage in the first step. By using this thing, we can easily find general formula I is equal to V by R. For V, it is a EF, field voltage. For R, it is a RF, field resistance. By dividing these two things, we can find the IF value. So IF can also find by one more formula. It is nothing but current density into area of the field current. So del F into AF. By product of this thing, we can find the field current. We had a two formula here to finding the field current value. For the second formula, the del F is almost lies between 3 to 4 ampere per mm square. So these are the constant and assumption. So go with the sixth step. It is nothing but a field turns, number of field turns calculation. So to determine this thing, you just first of all gather the full load field MMF value. So full load field MMF ATFL is written by IF into TF. So for A is declared as IF, for T it is declared as TF. So this is the equation. Rewrite this equation to find the TF value. So when we keep this TF on this side and IF on that side, it will form this equation. So this is the formula for finding the field turns. TF is equal to full load MMF divided by IF value. Then the seventh one is nothing but copper losses. To determine the copper losses, it is declared as Q here, the power of losses, QF, field copper losses, QF. It was founded by I square R, same formula. So, but it is in the field formula. So, I square F into RF. So, we already find the RF in the second step itself. Substitute the RF value here. So, you got this equation. After that, conclusion you have to write here. So, separate one I and the TF value. So, it will become this I is declared as A and TF is declared as T. So, AT is formed, full load field MMF into one IF is remaining, that is here. Then with rho L MFT divided by AF, the same data is there. With this continuation, next data of 8.1, which is nothing but a temperature rise. Okay, here the permissible limit of temperature is by taking a type of insulation. So insulations will depend on the rises. So for that we cannot consider this in insulation aspect. When go for the winding aspect, only a copper loss will produce the heat and it will develop the temperature rise. So go and handle with the copper losses. So the loss dissipation, QF here, just see the content. For the loss dissipation, the equation should be declared with Q, small q suffix here, is nothing but loss due to field coil. That is declared with capital QF. Small QF is loss dissipation, capital QF is loss due to field coil. Then divided by a dissipating surface, it is nothing but S. So that S has been calculated by using this equation, which is nothing but 2 into LMFT, mean turn length, then in product of HF plus DF, height and depth of the field. So by solving this equation, you can find the S. By dividing this value, you can find the small QS, which is nothing but loss dissipation. Then for this content, assume this value, we can also find the temperature rise by using this formula. After finding this QF by S, that thing is nothing but cooling coefficient, CF. CF is calculated by using this formula. It is armature voltage, then all other things are numerical. This is nothing but a clearance value and a constant. So by proper substituting of value, you can find the CF. So you have to multiply these two things and declare the temperature rise. It's nothing but theta is equal to QF CF divided by S. Then the last step of 9 to 1, it is nothing but assigning a clearance value, a proper value of clearance between the adjacent field coils. So that is a minimum clearance should be applied for this content is nothing but 15 mm. So generally we can consider a 15 mm for adjacent coils as a clearance. By using this thing, we can properly design a field coil. That's all, peoples, for the complete designing steps of field coil. when the questions ask like this, give the clear procedure or write the procedure for design of field winding, you have to declare all the 9 points here. With the 9 points, we also have a problem to solve. So let's go and see the problems in design of field winding.